So PRIMAger is the second instrument. It's essentially a Euro-provided instrument with groups from France and so on, and the UK. This on the right here is a preliminary design of the appearance of the instrument. It's going to change slightly, but more or less it's an optomechanical box with mirrors and filters, with two colder boxes which contain the focal plane array, one for the hyperspectral imaging system and the other one for the polarimetric imaging system. So in one view graph, this is what PRIMAger is. It's on one side, it's a hyperspectral imager. I'll explain what this really means. It provides images in the range 24 to 84 microns with a spectral resolution of approximately 10. It works in total intensity and has a full width at half max that's ranging from 4 arcsecond to 7 arcsecond on both edges of the band. This in the focal plane, this is the footprint. It's called PHI. This is a footprint of the two array that realize this coverage of the spectral range. And on the other side, we have the polarimetric imager, PPI, which comprised of 4 individual bands, which are 4 broad bands, are called 4, from 91 to 230 micron. It's important to realize that both focal planes, so the 6 arrays, operate simultaneously inside the field of view provided by the telescope, this 42 by 24 arc-minute field of regard that the telescope provides, but their relative positioning is fixed. So if you want to map an area both with the PHI and the PPI, you will have to move that footprint on the sky either with the beam steering mirror when the field of view that you intend to map is smaller than the accessible field of view in the telescope field of regard, or with the telescope. And that's why PRIMAger is really a mapping instrument that can realize small maps with the internal beam steering mirror, and larger degree scale maps with the spacecraft scanning combined with the BSM for internal modulation. Now, as is shown below, the two kinds of array are slightly different, so I'll go a bit more details on them. On the hyperspectral side, the spectral information is gathered through the use of the linear variable filter. So it means that on top of a spatial variation in the long direction, this part, the top part of the array is looking spatially at a different part of the sky than the bottom part. You also have a spectral variation in the sense that at the bottom you're getting low wavelengths of the range, and at the top you're gaining higher wavelengths, larger wavelengths of the spectral range. That means that to achieve full spectral coverage, a source needs to be scanned from top to bottom or bottom to top of this array. So there's a minimal span that you need to reach before you start acquiring a full spectrum of a source. And typically that minimal span is the length of the array, which is 3.5 arc-minutes. There are 2 concurrent developments of linear variable filter that are going on right now that will lead to the selection of the final filter. We are aiming for an R of 10, but when considering whether you want to use the hyperspectral imager or the low resolution spectrometer on the far side, you should see whether your science case is robust to an R of 8, because that's typically the number that we are looking at right now. On the polarimetric imager, the situation is slightly different. We're still using kits, but we're using antenna to make to realize pixels that are polarization sensitive. And so you can think of each of these pixels as being equipped with a polarizer that selects light according to 3 different directions. So the signal that comes out and the maps that comes out of PPI are in effect polarized map all the time. And the total intensity and polarized intensity maps are reconstructed by data processing by combining the signals from these 3 different pixels. So here as well, we need to map the sky in order to sample every pixel of the sky with the 3 kinds of different pixels that we have in our focal plane. So the mapping strategy of PRIMAger, I've said it before, but I'll say it again because it's important. There is no staring mode. This is snapshot mode of PRIMAger because we need to move the array on the sky to recover the information we need, be it spectral information on the PHI or polarimetric information on the PPI. Given the size of the array, in fact, we have 2 strategies to map. When the fields of view are smaller than the accessible field of view or field of regard given by the telescope, the beam steering mirror will suffice. We haven't yet finalized the kind of trajectories that we would use, but the beam steering mirror is very agile. One important thing to remember is that if you want to map an area with more than one array, if that's your science target, you need to take into account the fact that these 2 arrays are displaced from one another by a non-compressible distance. And so your map needs to be larger than your target area so that the common area is the common area seen by all of the arrays of interest achieves your intended mapping area. So typically, if you want a 20 by 20 arc minute scale arc minute map with all the PPI arrays, you need to do a 30 by 30 arc minutes, well, 24, which is your max, but at least go 30 arc minutes in one direction to make it. When you're looking for larger areas, tens of arc minutes to a few degrees, we're going to scan with the spacecraft, and that margin, which is due to the arrays not looking at the same place in the sky, becomes negligible with respect to the motions you want to do and the efficiency of the spacecraft. Obviously, PRIMAger with operating at 200 and in the 100 microns with a telescope of 1.8 meter is sensitive to confusion, and confusion is a strong limit. But you can read in those 2 papers, we're already developing strategies to fight this confusion. The important aspect to realize is that there will be lots of prior catalog to start from when we will start observing the sky in deep surveys with PRIMAger. So there will be lots of prior information that we can use to beat the confusion, and the simulations that we've been doing so far support that statement that we can go below the classical confusion limit provided by our telescope. So the last 2 tables that I'm showing are sensitivities and characteristics of PRIMAger. These are implemented in the time estimator, so you will have them for reference, but you have a tool to use them. There will probably be some minor changes to the numbers here that describe the arrays because we are still working on the design of the instrument, but none that affects really the feasibility of the science case that you may want to develop. And the sensitivities are here, both in total power and polarized power, both for point source flux density and surface brightness flux density. They all correspond to 5 sigma background subtracted fluxes. And I give you here, if you want, the scaling that you can use to go from this case, which is 1 square degree, 10 hours, to your science case. But again, these relations are implemented in the time estimator, except for the surface brightness, but I think it's just a matter of time. And so that's the summary. So PRIMAger is a high sensitivity mapping instrument. You have a choice of hyperspectral imaging and polarimetric imaging. You will always get both channels operating. So in a sense, if you're only interested by polarimetry, you get serendipitous data in the hyperspectral imager, and reciprocally. And if you're interested by both, well, you need to design your observation strategy appropriately, but it's not too complicated. That's it. Thank you.
Great, thanks, Mark. We'll take any questions that folks have. Andrew, go ahead.
Yeah, sorry. This is maybe a bit of a question about operations, but are there thoughts here about how well we can model the zodiacal backgrounds and be subtracting those, and any sort of observational strategies that are going to be implemented to try to help model that time-dependent background?
Um, well, the zodiacal background for the moment is taken into account in the sensitivity estimation as a nuisance parameter. Uh, uh, Granted, it's a certain level of the zodiacal background, and so uh, the case that we are showing here and in the time estimator is I would say a favorable case because it's for an extragalactic observation. But if you want, I can provide you with some, what would happen if you were going to point within the ecliptic, for instance. Um, I think in terms of variability, uh, there is spatial variability. There is a gradient in the zodiacal light, but I think this we will see as an object in the maps. I'm not sure the observations we will make would be on timescales where we see the variability of the zodiacal light, in the sense that, going back to a similar pointing a few weeks or months after we could see it. But during the observation, I don't think we have timescales that are affected by that. So I think we are considering the zodiacal light as a foreground, as a stable foreground, possibly structured or at least with a gradient on the observation.
Yeah, I mean, maybe I could add a little bit to that. So regarding the question of background subtraction, all of the mapping with, say, PRIMAger, or the chopping with Virus, or the mapping with Virus, that all essentially automatically subtracts a smooth background from the scene. And then the question is, as Mark said, is there some structure that from the foregrounds uh, that will be imprinted in the map? And the answer is yes. If there is structure, we will measure it. There isn't, as Mark said, there is not much structure in the Zodi. It's pretty smooth, but it is true that there is some, as we go around in our orbit, there'll be some variations in the Zodi from the position in the orbit, depending where you're looking. So,
Mhm.
but all that should be smooth and is subtracted by the very nature of our map building and our chopping. Maybe that helps.
Yeah, it does.
Yeah,
Can I ask one other follow-up question?
yeah, I think so.
Yeah.
Um, uh, Right. Okay, so that's telling us what the background is, and this exposure time calculator has these numbers that you posted on the web and showed on these slides. Have you separated out the overheads in a way that's easily accessible if people wanted to vary the depth that we're going to in a way that's honest to the overheads? Like if you just divide by square root of time, like if I'm thinking about pushing towards the overhead dominated limit, is there a good way of understanding when we hit the overhead dominated limit? Is that somewhere that we can access?
I mean,
Um,
for very, very bright things, you want to do very bright measurements, or
Yeah,
bright
I
if you
think
want to do shallow measurements, yeah.
shallow. Yeah. Well, yeah, we should probably. I mean, okay, Prima doesn't have a lot of overheads. It's very agile. It's not like Web, so so even for very rapid measurements, but we haven't, I guess, looked carefully at exactly where that limit would be. We could take an action to look at that, but um, yeah. So maybe if you want to send some ballpark depths that you're interested in, we could think about what a scheme might look like.
I I I see Margaret has her hands raised, but I can uh, complement. In at least there is one case in the Fires estimator, because it's in the presentation, where it shows that your source is so bright that the observation is overhead dominated, and you may want to switch to high resolution mode. On the PRIMAger side, I haven't tried to do this. In these numbers, the overheads are taken into account, and since this is a 1 square degree map, the overheads are essentially due to the fact we have to brake, step, and reaccelerate the spacecraft to do the scanning. And this slightly depends on how big the map is going to be. Now, my advice is at this stage is to consider that the scaling that we propose scale the overhead as well in a way that is representative. It's true that when you go to the small map modes, you don't move the satellite anymore. So in principle, you have no overheads due to these motions, but you have some which are due to the fact that the common area, which is mapped by 2 arrays, is smaller than the area that you need to map. And so you have effectively an overhead there, even though you get useful data. It's just not as complete as the rest. So my advice is it's a fair question, but at this moment, to define the geo cases, it's probably not necessary to try and think and optimize this. And the scalings we provide should give you the right estimate of time to define whether your case is feasible or unfeasible, because essentially that's the dividing line. You know?
Yeah, Margaret, go ahead.
Yeah, I just wanted to get some clarity, and maybe this will be happening with the ETC calculation, but do the ETC calculators just capture the science integration time?
No, that's the whole integration time.
Okay, all right.
At least since we're scaling, we're scaling from the case that I've highlighted, and that case is the whole observing time. It's the wall clock time to get to get the observation.
Okay.
But
it
yeah,
includes
but
the
I
overhead.
think it's fair that our ETC calculation does not include observatory overheads like calibration.
Gluing
Morning
and
No,
things
check.
like
yeah.
that.
So
Yeah.
that but
Acquisition is not there.
yeah, and but that is we expect for PRIMA for that to be a modest time, like 10%.
Right. Because we can get places quickly. Yeah, I just wanted to get some clarity. Also, the ETCs are just sort of a very requirements-based level. And, you know, as the observatory evolves, things will have higher and higher fidelity because we're offering things before we have all the details of everything going into it. But these are really good, thoughtful questions, Andrew. Thank you.
Matt, I was wondering if you would also say something. We had a question from the previous session about what we are thinking in terms of the ability to be observing targets in both FIRUS and PRIMAger. So what does it look like to be switching from one instrument to the other?
That's a good question. So we observe with one at a time. So either all the pixels of PRIMAger are being read out, or all 4 bands of FIRUS are being read out, but not both. From what I saw from the question, there was a question about maybe finding targets with PRIMAger and then following them up with FIRUS. And that's absolutely something that we envision, but it wouldn't be a real-time type of activity. You know, the PRIMAger data would come down, the maps would be constructed, sources identified, and then you know, in a subsequent observing campaign, you would have FIRUS targets from that PRIMAger map, but we don't envision that there would be a rapid you know, extraction of sources and then follow up with FIRUS, unless there's a strong case for it. But you know, we don't envision that there would be a time domain type capability where a FIRUS or PRIMAger finds something and then you track it with FIRUS. If someone makes such a case, you know, we could consider it, but that's not what we're considering at the moment.
So also, if you just know your source already and you intend to observe with both instruments, do you have any idea of how quickly one might be able to switch from FIRIS to PRIMAger? So
Well,
do
yeah,
you have the sense that you could be observing those back to back, or that and if you do that, maybe what is the pointing requirement? And if not, sort of like how might we envision observing blocks with PRIMAger and then observing blocks with FIRIS?
yeah. We're definitely envisioning blocks of PRIMAger and blocks of FIRIS. And where a block is of order multiple days. It doesn't necessarily have to be that way, but there will be some switching time. We don't know exactly, but I'm gonna guess that's measured in fractions of an hour. So we're not gonna want to do it multiple times per day, right? It's not but certainly on a few day time scale, I could imagine we could switch between FIRIS and PRIMAger. Was that a question that came up in the context of a time domain, time critical type of?
I'm not actually sure what the context was, but that's a useful answer.
Yeah.
Thank you.
I mean,
Okay.
I think it's worth noting, as Mark said, for individual sources, for individual point sources, especially, there's not much benefit to using PRIMAger. PRIMAger is really for mapping. If you want an individual source, you're just as fast with FIRIS, maybe a little faster, and of course you get the full spectrum. Of course, for polarization, that's a different story, of course, but PRIMAger is really for mapping, for
Yeah.
rapid.
Andrew.
So can I ask about the wide area mapping scan pattern? It looked like it was like this horizontal line scan back and forth, I think was mentioned. Is that scan direction being set by the linear variable filter on the hyperspectral side? And what would a scan pattern look like as one pushes to larger fields? Like you mapped it out for a 1 degree squared, but if one wanted to go bigger, like what is sort of the limitation on what the scan pattern would look like in largest fields?
So I think the scanning patterns may be limited by attitude constraints of the spacecraft, in the sense that we need to keep we will necessarily need to keep some angle with respect to the sun. And so of course it's usually expressed in degrees. So it means that probably if you want to make a 10-degree scan, there's only one direction in which you can do it, which is along the great circle. Now, coming back to the second part of the question, indeed, what we need in hyperspectral mode is that a pixel in the sky, sees all the pixels along the long direction. But that doesn't necessarily need to see them in one go, doesn't necessarily need to see them vertically. The important thing is that it is seen at least once, and probably more than once, by a pixel on each of these lines. So that gives us some freedom on the scanning direction. And most probably, in fact, what we will do is try and implement a beam steering mirror pattern within the spacecraft scanning to ease that constraint. We have in principle a constraint on the polarimetric side that there's more symmetry, but it's not complete freedom as well on the polarimetric side of the scanning pattern. But then the spacecraft, Matt was saying it's agile, but we have to be careful that trying to implement something else than cruising along great circles needs much more control, and it's probably not something that we will want to do. So when we go for a large map, I think you have to imagine that it will be a combination of these back and forth with the spacecraft, with an internal pattern superimposed with the beam steering mirror.
Mark Booth, go ahead.
Yeah, so you've been making this point that this is kind of a mapping instrument and not for kind of point sources. So I was just kind of wondering because I didn't realize that when I was trying out the ETC the other day, and I was kind of putting in numbers for like a survey area of 2 square arc minutes. I presume that the numbers I was getting out are then just kind of nonsensical. And is there like what's the kind of lower limit on the survey area that can be used in that?
Well, for PRIMAger, I would really recommend not doing maps smaller than a 10 by 10, something like that. I think below that you start spending a lot of time mapping. Well, unless you're interested by only one wavelength. If you want to map a small area in one band, then it makes sense to do a very small sort of dither with the beam steering mirror around your source, and that for the PPI. For the PHI, if you want spectral information, you need to at least move by a full array and a bit more, which is your mapped area. But as soon as you start to be interested by more than just one band, the spacing between the arrays is such that you will need to make a motion by 5-10 arc minutes, and so I recommend that the field of view is a 10 by 10 arc minutes minimum.
Thanks.
One thing that we may say is that we hear from the instrument teams where you can contact us if you have specific questions about science case. It's don't hesitate to do that rather than trying to figure things out with few information.